Well, it's a whole new experience, right? So we are running these live from the. I mean, it's always live, but it's like this time we're in the same place, in the same the London office.
Yeah. And even colleagues who are joining us live on YouTube now.
Have you booked this now? Because I booked it.
Yes, we have.
We have booked it.
Oh, God.
Okay. We'll edit this out
even
as well.
more real.
Exactly.
That's brilliant. Good.
So after we just talked about this briefly, right? We were 15 episodes it took us to make it finally happen, to be at the same place at the same time.
But it's unbelievable. It's fantastic. It's actually a bit of an awkward setup because because we're used to have our own desktop independently. So it's been tricky, and you can see the consequence of all these last minute preparations. But it's great to run it from the same room. That's first, after so many months. So really good. So maybe we should do another one before episode 32, shouldn't we?
Hopefully, it won't take us a year and a half almost to do it the next time. Please let us know in the chat if sound is coming through okay and everything else is looking good. So we had to scramble a little bit, as we said in the beginning, to set this up. So it should be fine. But if not, then please let us know, and please also excuse this camera is very high up for this, so we might be looking at our screens a lot, and then it seems like we are not in the mode of doing something else, but it is unfortunately a little bit of a
we have to create to have a studio to do this kind of things more professional. That's actually great for the time, the preparation time that we've had, isn't it?
Exactly. Yes, it's good.
Good.
So welcome everybody, and happy to have you all here for Going Meta episode 16. Let me add your screen in, Jesus. So semantic similarity metrics in taxonomies is going to be our topic for today. So taxonomies is a topic we have talked about a couple of times now. So it's like a couple of episodes have mentioned taxonomies recently.
True. That's true, and actually probably in both of them I've mentioned this idea of there's some semantic similarity metrics that I'm not going to be talking about today. Well, today we're going to talk about them finally. So yes, we probably put less the focus on analyzing the taxonomies. We know now what taxonomies are and how they help us organizing the content in our graph. What we're looking at today is double-clicking and drilling into these kind of standard semantic similarity metrics and how we can use them in NEO. So that's the plan for today.
That sounds good. Sounds interesting. If you have, as ever, any questions, anything we can talk about a little bit more, then obviously use the chat. Happy to discuss a few things in break time. Should we have some time to discuss it, and then we can take it from there. But we usually start with some intro slides. So
perfect. Actually some familiar ones, because I think we opened last episode with this one, and we hopefully agreed that taxonomies are a great way of making knowledge explicit, because when we create a taxonomy, when we classify whatever corpus of documents or even human, or not human, but animals, living what do you call it, living beings in in a classification of species, we're kind of making explicit our understanding of that particular domain. So that's there's some usable and programmatically usable knowledge in a taxonomy, and one of the things that we can do is measure the similarity between elements in it, right? And as you can imagine, well, it's I hope it's readable. This one makes it a bit darker, but the idea is that when you organize things in a taxonomy, which is a tree, obviously, sorry, a graph is a tree is a type of graph. So we can answer questions like, how similar is in this case a turtle to a crustacean or to a spider or something. So you can probably see that a turtle is closer to a lizard than it is to an arachnid and a spider, right? So and that's fundamentally based on as you can imagine, path computations, right? Distances in the graph. And also it's important at what level in the taxonomy does this distance take place. And actually this is something that academics have studied, and they've come up with some metrics. Actually, they come from a very particular context, which is the linguistics and in particular WordNet. And so these three metrics that we're going to be talking about today, which are the ones that have been implemented and that you can use in NEO, are ways to define the similarity between two elements in a taxonomy. So we'll look at them in detail, one by one, and also understand how they can be used in NEO. So, like I say, they all come from the linguistic space, and they have been implemented over WordNet. WordNet is a linguistic, it's called a database, but a collection of elements that you can use, among other ways, through Python, and that's how we are going to start to try and understand each one of them, and again, how we can extrapolate this idea to our own taxonomies. So not only WordNet, but any classification that we might want to use on our data. And I will reuse some of the elements that we have seen in previous episodes. So let's get started. Okay, any questions? Does that make sense?
So it does make sense. These three algorithms, I guess, are available in Neo4j.
They are. I mean, the thing is, if you build from source, they're in your semantics, right? So if you build from source, they're there. But I would recommend, wait till the end of the week, and it will be included in the next release. So it's if you're really impatient, you can get it just today. But probably the best is to wait till the next release.
Yeah.
Right. So as always, I'm going to jump into some code, and I was going to say that why not starting with a notebook? Tell me, Alex, if that's readable. Maybe I can make it a bit bigger. So this is just a Python notebook where we are going to use a couple of simple elements of WordNet. So WordNet is part of the NLTK package in Python. And as I click, you see that I'm importing the NLTK, which is for Natural Language Toolkit. So it's a very popular, I'm sure many of our Python users are very familiar with it. So what we're doing is we're importing the WordNet component. And before using that, we have to download it so that it basically imports the whole, I think it's a lexical database. If I don't use the right terms, forgive me, because I'm not an expert in linguistics. But the idea is that the central element in WordNet is what's called a synset. A synset is a set of synonyms, right? So it's a collection of words that have a shared meaning. And best thing I think is to describe this with an example, right? So if I'm looking for this collection of synonyms, this synset for the word dog, and in its function noun, as a noun, apparently dog can also be a verb in English. Well, we see that we have a collection of them, so it can have multiple different meanings. We're going to take one of them, the first one, which is probably the one that we're all thinking of, right? Okay. So if I take this is a unique identifier for this specific meaning. So let's keep in mind the synset is a semantic element. So if I look at it, I can say, okay, let's store it in a variable. Let's take this individual synset and give me the definition, some examples, and the lemmas, which are actually again, linguistics terminology, is the words that actually are part of that synset. So, well, as we were expecting, this is dog as in our pet, our animal. That you can see the definition here. So it's a member of the Canis family, that has been domesticated, so on and so forth. And we have a number of words that actually converge, if you want, into these synsets. There's the word dog, of course. There's domestic dog. There's Canis familiaris. So these are all words in WordNet that happen to have all the same meaning, which is this the one defined by this synset dog, right? Right. So now here's where the taxonomies come into play. So these concepts, let's call it like that, or these sets of synonyms, are organized in a taxonomy. So we can say that a dog is a subcategory of something more general, or has some more specific concepts. And we can explore that, that notion of a more general or more specific term by following the two functions, hypernyms and hyponyms. So if I print quickly going to see what that means. So hypernyms go up in the taxonomy. So a dog is a more specific category than canine or domestic animal. Domestic animal might include other, not only dogs, but dog is a type of. So that's where the taxonomical
So like
relationships.
in a tree, almost
Correct.
Like the one you showed earlier.
If we go back to our tree here, it would be something like we have our dog here, which is a subcategory of domestic animals, and so on.
Exactly, and then it goes down into like specific species or
correct. Let's see what this shows, because the hypernyms. So we have you're right, specific what's it called, specific breeds of dogs. Yeah. So all these are types of dogs. So again, you see that we have a taxonomy there, and we can do something similar, and because we're going to go to similarities. Let's take another one, and I take cat, do exactly the same. So I get the synsets for cat. There's a number of them. I pick the first one, which is, I'm doing exactly the same we did before with dogs. So that's the feline mammal. I can even add the, how we call it, the lemmas, right? So if I rerun that, we'll get the multiple words, in this case, not too many, cat and true cat, or whatever. That's what's in WordNet. Yeah. So these are the words that actually, I don't know if implement, I'm using software terms, but these are the words that share the same meaning, right? Yeah. Anyway,
so I guess there must be some kind of animal that are called something like cat, but who are actually not a cat. Like, I think, I don't know if this is only German, but only in English, maybe koala bears. Is what it's called. It's not a bear.
Exactly,
but that's
totally. So that's so these are just two examples, and where we wanted to go is to the definition of these metrics, right? So we see that WordNet actually implements the three metrics that we mentioned before. So if we go back to our description, so we have path similarity, and path similarity is defined literally as the distance in the taxonomy between the two elements. So let's say we have cat and dog here. Mm-hmm. So we're going to compute the path, as in a path in a graph. And then we're going to apply this function. So because we want the similarity to be, in this case, the path similarity between 0 and 1, we apply these factors. So we did 1 divided by 1 plus the distance, and that's to avoid, I suppose, division by 0. But this is not my formula. This is defined. And actually, I had a link here to the documentation of the NLTK, and if we go to path similarity, you have a nice description of what this means and how to use it. Basically, the examples have been taken from this manual. So
should we share this link?
Yeah, absolutely. Yeah. So how can I do that? So
if you post it in there, then I can grab it and.
Perfect. So there you go. Okay. So and I was going to say that these methods for similarity are available in the Python NLTK, and we can do something like this. So we can take dog, which, if you remember, contains the synset for dog, as we explored here. We have the synset for cat, and we can apply the function path similarity, and that's going to compute this distance, right? And unfortunately, WordNet doesn't offer a tree view. I mean, we see that there's a taxonomy, but all we can get is this metric. Yeah. So that's this path-based path similarity, as it's called. The other two are also present here. One is called LCH for Leacock-Chodorow, and you will see that each one of them returns a different numeric value, indicating, and the other one is WP. So you can compare two items, and and that returns a numeric metric that basically tells you how similar or how different the two are. So that's the idea. So they're there, and that's these are three standard. Yeah, go ahead. Sorry.
Yeah, and because we now saw three different values. One was 0.2, one was 2 point something, and this one is 0.885.
Yeah.
So you don't get the same values depending on your algorithms, because as you showed earlier in the mathematical function, or that is being calculated in the backend, the value will be different, and that means you have to know which algorithms are you applying to interpret that value, and okay, is is that close or not?
Correct, and also, I suppose they're useful in different contexts, and they take into account different things. So yes, for example, you've noticed that the first one is always going to be between 0 and 1. That's not the case for the other two. That can go over 1. So you probably have to calibrate them a little bit in your examples and understand what. But we'll go into details in a minute. But that's totally right. And well, the thing is, these similarity metrics, I think they're extremely useful, right? Because it's a way of adding a numeric value to a similarity. And remember that what we're doing here, and like we've used in other examples, a taxonomy can be useful to classify documents. It can be useful to classify news. It can be useful to classify a product catalog. You can even have multiple taxonomies, because that's we've started with this example here, but that doesn't need to be a single tree, a single classification. We can have multiple ones. And these all play quite well with this scenario. We'll have some of those. But these are, as far as I know, I've not been able to find any use of these outside WordNet in these type of libraries. So I said, hey, that's something I want to have, because I use taxonomies a lot, and I want to compute the distance. We've used it in some cases, right? Remember when we overlaid that taxonomy and ontology on top of our articles, we did the NLP, we annotated them, and we said, because you're reading this, you might be interested in reading that, or you this and that, how similar or how. Well, that's exactly what we're after. So these are the functions.
Or even the previous, not the previous, the 2 episodes ago.
Yeah.
When we talked about matching these different ontologies together, we could have also used this recommendation or a similarity score in the end and say, okay, we know that these 3 ontologies come together now into our super ontology, and we need to calculate, because there were gaps, right? If you remember, in the overlay, they didn't match exactly, but we could then go and say, okay, how similar are these, and is there a perfect match, or how close do we think this match is going to be, and then decide, okay, this match is close enough that we can say, okay, this is the same thing, and this maybe not the same thing. So we either have to work around somehow.
So many. I mean, I find so many. I really can't believe that these are not available, in general for any kind of taxonomy. And maybe it's my ignorance. Maybe it's being aware. So anyone, and if you and any of the people listening to us are using any particular techniques to compute similarity in a taxonomy, I'll be super keen to hear more about it. What you say, it's exactly right. So you combine 2 ontologies. What was the 2 taxonomies? What was the impact did that new taxonomy bring these 2 elements closer because there's new paths? I mean, really many uses for these. So I hope that as a context that sets the scene clearly. So what we're going to do now is, okay, these functions. I mean, we agree that they're useful, and we'll go a little bit into the details, because I know there's some complexity in some of them, but let's look how we can use them in Neo. And for that, I'm going to use first a simple example, right? So let me, hopefully, there you go. So we have an empty database here, and we have our favorite way of importing a taxonomy. I could create a taxonomy manually and just build the categories and link them with a subcategory of whatever. But we know we have a quick way of doing it, which is importing some pre-existing one. And yes, as for this example, actually have copied. It should be here already. So that's the first element that you'll find in the repository for this episode 16, session 16. So there's one that someone shared in the past, and we used for the semantics documentation, and it's a pretty simple one. I mean, rather than going over the RDF version of it, let's import it and explore it. But basically, it classifies vehicles, Volkswagen vehicles, and types of engines. So if I take this ontology like we've done many times, and I take the link. Remember that we have to, I mean, this is the nice and human version of it, but it's HTML. So we have to go, actually, I can click in this case. I can go to the raw version of it, which is the one that actually contains the raw RDF, which is what I want to import. So I'm going to copy the URL, go to my browser, and as always, I'm going to call ntns onto import, and I'm going to pass the URL that I just copied and the serialization format, which is turtle. right? So I can make that so that it's readable. Of course, this is going to throw an error, right, Alex? You know my way of operating here. So I wait for the error because it comes with the solution. So I need to create an index before we can import any RDF. So I do that. And then I need to create a graph configuration. And remember that the graph configuration specifies how do I want this RDF taxonomy imported into Neo. And you're going to see that I can initialize that graph config. I can initialize it just by using the defaults, or to make it more readable, I'm going to specify that in this case, I'm not too worried about the vocabulary URIs. I mean, I am with the identifiers, but not with the names in the vocabulary. That's why I'm going to say I want to ignore them. And that's pretty much it. So again, all this code will be in the repo after this session. So we are prepared now. So if we get rid of that and we retry now the input, hopefully that should go through. It's told me that it's read the triples, imported most of them. Remember that the ontology importer excludes some elements that are not relevant for our case. But in this example, now we have a collection of classes, as you will see, that are, and actually I can probably say that I want to use the name as the, but rather than that, I probably want to see how they're organized in a taxonomy, like the subclass of. And you see that there is kind of a tree, a taxonomy, but as you know, the browser is not the best tool to visualize that. So let's go to Bloom, which should be here. And I hopefully have it ready. So all I have to do is create a perspective. I'm going to generate a perspective on my database. Let's use it. I really don't need a resource or the graph config. What I want is the classes. That's all I have in my model. And if we go to this exploration, we can say, give me all the classes. Give me all the classes. And I can probably expand them all, expand the subclass of, and we will see. And I had already, set before the hierarchical layout, which is particularly good for a taxonomy, as you can see. I mean, that's. I don't know if it's readable, but you see that there's. It's a pretty simple taxonomy, right? We have automobile, Volkswagen, because that's all we have in this small data set, and we have SUV, wagon, convertible, compact, and a sedan. And for each one of them, we have different models. So pretty simple taxonomy. And we have a couple of elements floating up here, which is the type of we have components, in particular the engine, and we have two types of engine, electric and gas, right? So I'm going to, I don't know, maybe move it down here just to, but well, anyway, you see that there are two independent taxonomies. So that's, and it's going to be interesting to see what happens when I look at the distance and the similarity between elements in independent taxonomies, as we were saying before.
So they don't connect at all. So you don't have well, I need to lean in a little bit. Say this one, the Golf, I guess, is comes with diesel or with a gas and electric engine.
Well,
so this is the connection we need to discover now.
Well, we're going to measure the distance and the similarity between them. We actually, in this case, we only have the classification. We don't have the individuals. So if, for example, you could have, hey, there's Alex's car, which is a Golf, and it's electric, right? So you would link to both of them. In this case, we're not going to use individuals. We just use the taxonomies, and we accept that sometimes, I mean, what you would do in that case is you get an individual, you get another individual, you get the categories that they belong to, and then you do the similarity between them. Yeah. So you would need to do one additional step. But in this case, we're going to stick to just the classes in the taxonomy. Yeah. So, okay, we have a taxonomy, and the kind of questions that we wanted to ask, like we did with the dog and the cat before, is well, how similar or how different is, for example, let's take a couple of them, these two SUVs here. So if I take the Tiguan and the Atlas, well, I hope them to be pretty similar, right? So I hope the similarity metrics to return, we can get rid of, well, we can leave it there. But I can do something like, okay, find an element, which is a class. In this case, I've used the default, so it's importing categories as classes. But you know that you can control that with the config, so you would rename things in the way you prefer. So there will be one with the name, we said it was Atlas. Right, so let's call this A, and there will be another call it P, another class, which has a different name, which we said it was T1. So let's make sure that I've spelled them correctly. If I return A and B, perfect. So we have the two. So what I want to do is, sorry, to return the nodes, but call the function, and this is what we've implemented in Neo Semantics. So there will be a function called N10s similarity, and you see the names already, right? Similar naming as in Python. So we have let's start with path similarity, right? So with path similarity, all we have to pass is the two elements A and B that we want to compare, and if we run this, we get 0.33, right? So that's again, if we look at it, the formula that it implements, we can hopefully go back here, and I don't need to go into the details, but it basically takes 1 divided by 1 plus the distance between the two, and the distance between them, actually, we have a quite convenient function here that returns us in the form of a path. So if you go to pathsim and you type path, that will return the path between them. In this case, they're directly connected, so easy. So the distance is 2, 1, 2, plus 1, that makes 3. 1 divided by 3 is 0.3. So that's the simplest one. And the good thing is it's simple, right? It's simple, it's pretty efficient, but it doesn't take into account context, right?
So yes, that's true, because if you then would say compare this to one of the other ones here, like a convertible or so, it would be, well, it would actually be, it would be different enough.
The question is, if I compare SUV to a convertible.
Oh yeah, that's a better point. Yeah.
So I would expect the path similarity to be identical, because there are distance too.
Yes.
Now, are these more similar or less similar than these down here? I would say that probably the further down you are, the closer you are, because you're already within a category, so you're kind of narrowing down.
True. Yes.
And the path similarity does not capture that, and it will return. I mean, if we do it, we said convertible and SUV. I would be surprised if we get something different, right? If we get convertible and SUV, I would get the same path, but I'm not interested in the path. I wanted the value. I get exactly the same value, and that's
all these top level, and then you get
exactly
the same value, but they are
and
convertible and SUV
are pretty different, exactly, and that's the idea that we were talking about here at the beginning, right? So if you compare, I don't know, animals and plants, they're probably one hop away. Yes. They're very, very close. Yeah. But this similarity is very, very different from the one between a snake and a lizard, right? So that's why the other metrics, take that into account, and that's why it's a good start, the path similarity, and for some cases that's good enough, and it's all we need. But let's look at Leacock-Chodorow, because that exactly it goes one step in that direction. Basically, what it does, if you think of it, is still very much strongly based on the distance, because it takes the distance, but it divides by the depth of the taxonomy where the element is. In this case, the depth is the same because they both belong in the same taxonomy, but maybe they could be in different taxonomies, and then the depth would be different. But again, it goes one step in that direction, right? So it kind of puts into context, and the bigger the taxonomy, the most important a short distance is, right? And we can experiment with that a little bit. So if we go here, we can do exactly the same with it with Atlas and Tiguan, but instead of instead of path similarity, we can do the LCH similarity. And we will get a different value, right? As we saw before, this is not expected to be between 0 and 1 because it applies a logarithm there. But still, I mean, how can we tell that this is affected by? Why don't we do that? So this distance would be the same. I think it would be the same, right?
We do convertible to SUV?
sim.
The same.
Yeah, because they're in the same taxonomy, right?
Just one step up.
Exactly.
Yeah.
So again, it doesn't distinguish that, but if it takes into account the depth end to end of the taxonomy. So if we add one element to the taxonomy, and that's something that we can do pretty easily, adding a small fragment of RDF. So what I want to do is, okay, I'm going to come and define under Tiguan my own special type of car, which I'm completely making up, but I can do, sorry, not much. I can call N10S onto import, but this time I'm going to inline a small fragment, again, of turtle. And I'm going to copy this time to avoid mistakes. So if I paste this, what I'm adding here is something I call Tiguan Special, which is another class, which is a subclass of Tiguan. So I'm adding a new node to the taxonomy just under Tiguan. So if I spelled it correctly, this has imported 3 new triples. And if we go to our, that should expand. There you go. So we have a new element here.
Yeah. So
hopefully that should have made, we can get rid of this line now, but this should have made a difference to the to these distances, to the similarity metrics, right? So if we now take these, there you go. So it's gone up.
Have to start at the Tiguan Special.
Oh, good point. Well, no, not necessarily. Not necessarily, because the same elements, the same pair of elements at the same distance have been affected by the fact that there is another element in the taxonomy.
Interesting.
So basically what, I mean, and again, this is my interpretation, because it's a richer taxonomy, maybe a shorter distance is more meaningful. The bigger the taxonomy is, right? I suppose it doesn't take into account the level, but I suppose, well, maybe some linguists can help us here, but that's the way it's defined. So it's really affected by the depth of the taxonomy. I suppose it's interesting also when there's multiple taxonomies into play, and we can look at that actually.
So it does take into account that there is something coming after the actual node.
Before or after, yeah.
Before or after, so the two nodes we are comparing. So which the other one didn't care much about. So
yeah, because if you see here, it takes. I mean, it's not just the depth of the element; it's the depth of the whole. This big T is the depth of the whole taxonomy, all the way to the leaf element. So yeah, maybe in this example it's not too clear, but it's the whole end-to-end depth.
Yeah.
So yeah, and actually, one thing that I wanted to show, because we didn't cover it before. If we go back to the path similarity, so we compare, for example, Atlas and Tiguan, and they were pretty close, and we could show the path. So we can expand that. Actually, for example, let's bring one that's at a bigger distance. Maybe we can do the Tiguan Special to the Golf. Why not? So we'll see if we take the Golf and Tiguan Special, you should see maybe something not correctly spelled.
Do refresh on the browser side.
I think it should be. I mean, let me see if I'm catching the A and B. Yeah, something's not matching. So Tiguan Special. What did I spell wrong? So class is Golf and Atlas Tiguan. Okay, let's try to find out. So Tiguan Special, if I click the name, oh, no white space between them, that's the reason. Okay. And then the Golf is just Golf, so it should work. But that's, so I think this is it. There you go. Yeah. So, yeah. So if I redo that, we should expect to see a longer path, right? But still, they're connected. So what's interesting, and we can see they go all the way up to Volkswagen, and the path similarity. If we look at it as the value, it will be 0.16. Now, what happens if I compare two things that are not connected, right? So there's an interesting default behavior. So if I compare, let's say, my Tiguan Special or my Golf, but I compare it to electric car or to gas car, whatever. Let's use electric in this case. So these are two categories that are not connected at all. So I would expect the distance to be, I don't know, maybe 0. There's no similar, not the distance, but the similarity. Are they completely, or maybe not, because that's the thing, and that might be surprising, but let's give it a try. So if we compare the Golf to electric car, and we do the path similarity value, well, it's not. It's surprisingly, in this case, shorter. Well, it's more similar. So it's shorter distance. No, it's not. It's just a little bit less, but still less. And there's an explanation for that. And part of it's going to come.
So it kind of tells you. What was it? The Tiguan Special and the Golf are more related than the Tiguan Special and an electric engine.
That's correct,
but not by much.
Yeah, that's true. And the explanation is by the definition of the. Because look at it. I mean, what happens is that the algorithm, this similarity metric, creates kind of a synthetic node that combines the two taxonomies. So if you look at the Golf taxonomy ends in automobile, right?
Yeah.
And the electric car ends in component, right? So these are two taxonomies that are independent.
Yeah.
Now, is it fair to assume that all things, even if you have multiple taxonomies, are subcategories of a global, I don't know, let's call it thing? So everything is a subcategory of thing. Well, that's the default behavior, and that's again not me. That's let's go back to these. To this definition in WordNet, and that's by default it creates this, you call it simulate the root. So by default it simulates there's a common root to all taxonomies in your graph. But if you want that behavior to be disabled, you can say, hey, don't simulate the root, and you can do that. And in that case, you can. I hope that's covered here. So you can when you do the path similarity and you get the value. You can say, was it simulate? I'm gonna remember the syntax. Let's give it a try. It would simulate root, maybe. It would put it to false. And the similarity is 0, right? So we can say, don't implement that behavior, which maybe in my case it makes sense, because one is a classification on engines and the other one is on vehicles. So whether it makes sense or not in your case, you can take the default behavior or disable it and say, if there's separate taxonomies, similarity will default to 0.
Yeah.
Good. So that's the second metric. That was the Leacock-Chodorow. Interesting. One, and then the third one is also that's the one that really takes into account at what level the distance is taking place, and it defines, I don't know how readable is that, maybe make bigger, maybe we can go full screen, but it defines a notion which is the lowest common subsumer, which is like where do the two what's the common parent, the common ancestor, right? The lowest one. Because maybe if you're comparing the Golf and the Tiguan, maybe they converge at Volkswagen or they converge at automobile at different places. They can have multiple ancestors. So we're going to take the lowest one. That's the definition of the LCS, the lowest common subsumer or ancestor, right? So that's the level at which that happens is what defines these metrics. So you have the depth of each one of the elements individually, but then you also have the point where they converge. And by combining these three in this formula, so in this case, you find the depth of the lowest common, you find each of the individual depths, and you combine them in that way. If you think of it, it's ignoring the distance, but it's kind of captured somehow in the lowest common ancestor. So again, different metric, it will provide different values. So have a play and see which one is the one that works for your case. But we can, in our example, again, easily call it like we did before. Let's go back to the default behavior. And if we compare the Golf, which was the Atlas maybe, instead of path similarity, we're going to use Palmer. mention the name, but it's Wu Palmer and Leacock-Chodorow, right? So that's, if I've typed it correctly. Again, we have a new metric that takes into account the level. So if the example that we did before, let's take two similar ones. So when we compare the Atlas with the T1, capital T, we should get a pretty good similarity, so 0.75. And remember, they were at distance 2 because they have a common ancestor.
Yeah, exactly. The distance told us that's a 33%
correctly
similarity. So this is much better.
Exactly. Because and now the thing is, remember, we did the thing with, was it convertible?
Yeah.
And SUV, which are at the same distance as in path, but hopefully this metric is going to be different. And you see that it's lower. I mean, it's the same distance, but it happens at a higher level. Yeah. So they're less similar than these two are, and that captures these ideas. So I think 3 super useful metrics, and well, there they are. So you can play with them. You can use the graph. I mean, I guess there's still room for improvement, but that's where your feedback comes into place. So people have a look at this, and by all means, do share how were you comparing similarity, because maybe you, of course, if you don't have these tools, or if you're not aware of these metrics, maybe you can compute something in Cypher, right? Something that takes into account distance plus other factors, or you could even create your own metrics. But I thought these were pretty interesting ones and worth including.
And that's a good point. I think I saw in chat a couple of people were saying about weights and can these be weighted with properties on graphs in the Neo4j graph you have, or is this only working the projection? I think that's what you just mentioned, right? You calculate some similarities here out of it, and then you can totally enrich your data with these.
Absolutely. Yeah. And even I mean, these 3 are 3 kind of standards that come from WordNet and from the linguistic space. But yeah, I mean, again, I'm really interested in hearing if there are other approaches to this, because these are generally useful functions. So the possibility of extending these metrics is of course there, and I will be very keen to see what's the best way to do that. But yeah, distances can be persisted. I mean, this is working as a stored procedure. It works on the graph. It doesn't work on the projection. I know there was a question on that.
Yeah.
So this works on the actual graph, and this is more. I mean, I would not see this as an algorithm that you run on your projection, because if you think of it, you're taking 2 elements and doing a comparison. I mean, it's not like you're using these. I mean, why not? I mean, you could use this type of distance to cluster things. Maybe I don't know. These are ideas, but at the moment it's implemented as a distance function, as a similarity function, pretty much as you have a collection in APOC that does the similarity between strings, right? The Levenstein similarity and some others. Yeah. So this is one that takes into account the taxonomy and implements these metrics. Now it's probably interesting to add. I don't have an example for today, but in this case, we've. It integrates nicely with your ontology or taxonomy input. But in some cases, you create a taxonomy that's not the result of importing RDF. I mean, I never got it from RDF, so why not? You could perfectly, create, instead of calling it classes, you call it category. Instead of calling it SC or subclass of, you have your own names. So you can pass these to the. I'll share in the examples the syntax. But all you have to do is, if you don't want the defaults to be applied, you can say the class, the name for the class is this, and you give your name. The name for the subclass of relationship is that one. So there's a way of passing to the function. That's how I name things in my taxonomy, and therefore that's what this method should use. So that's also there. Like I say, I'm probably leave that for the examples in the repository, because I wanted to conclude with a larger example. And again, we can. What I'm going to do here is I'm going to delete this vehicle taxonomy. So I can do it by not relationship, but resource, and I'm going to detach. If I empty this, You might remember that in episode 2 or something like that, when we did the NLP on technical articles, we annotated them and then we overlaid a large taxonomy that we got from Wikidata. So that's still there. So I think I have the link here. So if you go to the Going Meta session 2 in the resources, we had a pretty large taxonomy of, I think it was software concepts. There were databases, there were programming languages, there were plenty of things, and then we could do recommendations between documents that talked about one or the other. So I'm going to use this one, and here's where I'm copying the URL as I did before, and I'm going to import that in my graph. So exactly the same. Actually, I'm going to copy it from here, and this is going to import. Oh, that's the wrong one. Damn it! Didn't want to do that. Let's delete again, and now let's import with the right URL, which I copied from here. Copy link address. Let's keep in mind that this is not an ontology; it's a SCOS classification. So I need to call the SCOS method. So boom, I put the address, and hopefully that should do it. It's a bit longer because it's accessing to the internet, but yeah, there you go. A few thousand, 11,000 triples. And now we have a larger taxonomy with a few thousand classes where we can find things like, if you remember, there was, I think Neo4j was there. There were classes where, see, there was preferred label. That's the terminology that SCOS uses, and equals or contains Neo4j. So there's a note, and yeah, this was Wikidata elements. So this is the name is the unique identifier in Wikidata, but we can use the preferred label, which is more friendly. That's the node that represents Neo4j. And you could expand it, and you probably remember that it was classified in a number of ways. It was a labeled property graph, it was a graph database, and so on and so forth. And you could keep expanding that and see all the related categories, right? So we have a much richer taxonomy. But I thought, just to conclude, to run a couple of interesting similarity metrics in this one, and this is a larger set, right? Yeah. So. Yeah, it's exactly the same, but I'm going to use a trick, which is copying from here, because I've already identified a couple of. Well, we could actually reuse that code. Why not? So we have this node, which is Neo4j. This is, let's name it Neo. So, and then we're going to find a MongoDB. So let's find MDB, which is another class where MDB, and we have to change this to Neo, otherwise it's going to throw an error. MDB preferred label contains, I don't know what the syntax is, probably something like Mongo something. So we return Neo and MongoDB. Here we go. So we have the two. We can now apply the similarity metrics that we did before. So that was something like 10s, similarity, and if we start with path similarity, I can compute that between Neo and MDB. And it tells us that it's 0.2. That's the similarity, and we could also get the path. And yeah, we remember that Neo is a graph database, Mongo is a NoSQL database, and they're both database management systems. Again, that's not my taxonomy, but it's one that we imported from Wikidata, and it makes sense, right? So distance 1, 2, 3, 4, 1 divided by 4 plus 1, 5, 0.2. So it's easy. I did that one because it's the easy one to compute, but we could enrich that with the other two metrics. Actually, we can call these as path, and we can return also antennas, similarity, LCH between the same pair, Neo and MDB. That's LCH. And finally, the third one is SNS similarity. Palma, again between Neo and MDB. That's so that gives us our three metrics, and we can do something similar, but now compare it with something a bit further away, something like I think there was programming languages. So maybe we can look for Java. See if that makes sense. Let's call this just to be consistent with the naming. Oh, there's multiple Java, so it's a JavaScript framework. Let's take Java programming language, for example, this one here, right? So the one that's preferred label is exactly Java. So if I take not contains, but it's exactly Java, that should give us is Neo not around? Oh yeah, because I'm returning just the one. Neo and Java. So we have the two nodes, and I can now compare them just like we did before. Let me copy paste that. So these would be, this is the one that contains the three metrics. I've been a bit picky with names, and I'm going to have to change all the. So if I return instead of MDB J, J, and J, that will give me the distances between that and the Java programming language, which hopefully should be smaller similarity. So yep. Neo4j is closer to MongoDB than it is to the Java programming language, and it happens in both. And we could play around with with the different levels, with adding elements, with comparing, instead of Neo4j and Mongo, comparing database management systems with, things that happen up in the hierarchy in taxonomy. But I think the idea is clear, and I hopefully see if there's any questions. But that's what I wanted to share today. So we have another way of getting value out of taxonomies, which I finished like I started, is another way of making knowledge explicit. Because we sometimes talk a lot about how knowledge graphs capture both data and knowledge, and sometimes it's unclear what do we mean by knowledge. Well, there you go. If you put a taxonomy, you're making your understanding of a domain explicit, and that's another proof that you can get value out of it, because it can help you driving similarity computation between things. So that's it. Any questions? What do you think? Well, maybe from you, Alex, is there anything that was unclear or that?
No, it was very clear. It was very interesting. I think it's looking at these algorithms, especially with similarity, is always very exciting. And I think it's a great value now with what we discussed earlier, right? When we think about, okay, you have your ontologies, maybe you have different kinds of data in your database already. You want to enrich that. You have maybe not your single source of truth. That's always like the one that's out there. It never is just one single source of truth. You always combine a couple of things, and you then say, okay, but now what do I do then? What's my next step? And that's
because that's totally. When you suggest add an ontology, add a taxonomy, the question is, why would I do that? It's good in the first place, because by putting it in written, by formalizing it, you're kind of making, even if it's just for documentation. You already think of this example that we had on the screen, right? So we have a good understanding of maybe programming languages, maybe database management systems. So that's useful in itself. Yeah. But if you associate with it, and you can, by doing that, now you can compute similarity. By doing that, you can do recommendation. So you have to always associate this component that can get value out of this effort, so that it justifies it, and so they translate it in business value in the end, which is don't do things for the sake of it, but for the value that they deliver.
That's super important, right? You have your data that's its own. Let's imagine it's its own little bubble. Then you add an ontology, and what does it add? Exactly. And now with this, I think it adds a lot.
Exactly.
Because then you can calculate things, and like a couple of people asked, what do I do with the data that's cut? What do I do with the similarity values I have? Add it in as a property into your notes, as an example, for example, or do something else with it, but add it in, enrich your data sets, and then you have more information, more knowledge, and the easiest is a product recommendation by saying, okay, here this product is similar to this one, and it's not only because in my product catalog says so, but also we added in an outside knowledge from an overall product ontology, let's say, and that says, okay, these two products are similar because they are from the same category inside the same.
Exactly, and you drive. I mean, these are generic metrics. I mean, they work whether you're classifying programming languages or you're classifying vehicles or you're classifying words.
Yeah.
So it's your taxonomies, it's your ontologies that drive the results of this comparison, and that's. I think it's important the angle that we touched on. I think it was episode 2 when we kept adding additional taxonomies. I mean, you can classify an article based on the topics that we've seen here, but you could also add technology stacks. Remember how we added the grand stack and the mean stack and all those. So, and I see that a lot. Some of our users are classifying, let's say, product catalogs according to multiple dimensions, according to multiple taxonomies. And you can combine them and you can use classification to drive similarity. And yes, recommendation is probably the most obvious one. Personalization. I mean, you're looking at that. Maybe I should recommend you to, or I should personalize your experience with things that are in a given radius of what your interest is. So I think there's immediate value out of this. So I would be looking forward to hearing.
I think I see lots of applications. Yeah, I would hope you two do. Maybe we close it with a couple of questions. There was one from Y. I think we touched this a little bit later in the presentation, but maybe let's go into this a little bit. But I think it's interesting is the similarity metric, which takes into account the density of a neighborhood of the node. I think this is a little bit what Palmer does, but is there
the density? I'm not sure. I mean, in these cases, because the density probably is how, for example, let's say these. That's a good point, because if this node here happens to have 3,000 children, so how good is that? I mean, how is it good to be similar between 3,000 as it that's a very good point. I don't think these ones take the density as in I'm interpreting that as the degree of a node. So and whether we kind of probably tend to think of taxonomies as kind of balanced ones. But what happens if one leg of the taxonomy is much more elaborated than another one? I suppose all these things can have an impact on these general purpose metrics. So I don't think these three take into account these density interpreted as that. But I'll keep looking. I think there's a couple more in WordNet. I'll explore the possibility of including them in Neosemantics as well. But if you have any suggestion, that would be an interesting one, because I think that's a very valid point, right? So the level is important, because as you drill down, you're refining. But it's true that if you have differently developed. I'm thinking here of Amazon product catalogs. I mean, I suppose if you go in very rare products, you will probably have at the same depth, maybe that's what the tree ends. But on the other on a I don't know, much more popular one, you might have an explosion of classes, and that's that would be an interesting exercise to see how these methods behave with these type of scenarios. Good question.
There was a question of using visualization to overlay the two, if you have two different taxonomies or two different ways of looking at the when we showed this in Bloom, okay, there's this one taxonomy, there's the other one. If you can overlay somehow, I think we didn't touch this today. Maybe for a separate session for some other.
And there is a risk, to be honest, with the visualization, right? So in this case, and that's why I use the smaller one because it's more intuitive. But the moment you start overlaying multiple ones, the visualization, you have to be a bit more precise on what's presented, because it can come, a bit too hard to visually understand. But Yeah, the visualization. I mean, that's why we focused on the programmatic use. I mean, the visualization is powerful, but it sometimes has limits. So I think the answer is, I don't think we have, I don't know, multiple layers. 3D, it would be great, but I don't think there's anything like that in Bloom at the moment.
Yeah. Then John, another comment on from John or question. What I really want is a way to chunk blobs of data in, have it parsed with LLM, outputting graph, also continuous auto creation of edges based on node content evaluated by LLM and other metrics. I think and other analytics. I guess this is more.
Yeah, I mean, we kind of show the building. It's true that we haven't. I've been a bit reluctant to go with LLMs because I think we have all other sessions that go on that. But yes, I mean, from that point of view, the LLM would act as a co-pilot that would do a number of steps for you. I mean, parsing the text, doing the NLP and extracting the entities and doing the connections. We've done that in episode 2. But yeah, it could all be bundled into a single effort. Maybe we could think of that as a topic for a future episode. But yes, I mean, in this case, we have and I think it's very important not to forget that you can learn a taxonomy, and actually we touched on that in, I can't remember, episode 7 or 8. There was a learning a taxonomy from a tagged collection of documents, but you have to combine that, and that's where I think with the virtuous approach is in a balance between the two. What you can learn from your data through completely automated approaches like LLMs and things like that, and what your experts curate and formalize in taxonomies like this one. I think we should not underestimate the value of ontologies and taxonomies as a way of capturing your enterprise and your business knowledge. And the combination of the two is where the really powerful solutions are. And maybe that's a good idea for a future episode. Yeah. So yeah, I guess we keep the questions, right? So
yeah,
I'd like to go over them one by one and see.
Let's do more. I think there were 2 more. There were some other discussions, but I think we can cover 1 or 2 more questions. So there, one from Isalier is what shall we do, or what is in the case where the edges have a weight value? So if you have already, maybe you have your own data, maybe you have weighted relationships already. Do you? I mean, obviously not with this algorithm, but in general, could you expand, or could you level up somehow and say, okay, I have weighted relationship, weighted paths, weighted.
What would be? I think you probably could. I mean, the thing is in a taxonomy, typically there's a subcategory of which is generic, and normally you don't have any weight. What we explored though, and I think we mentioned that I think it was in 2 or something like that, is that you can use that, and I suppose that could be generalized, and that's where the question goes. We were thinking of maybe trimming some and say, hey, don't use that branch to provide recommendations or to look for similarities, maybe because it's too dense, or maybe because it's too poor, or maybe because. So again, current implementation is purely standard, is as defined. So from that point of view, it doesn't take into account weights. Now the weights can be in the graph, and there's no reason why we cannot get value out of them. So good point. I would like to hear more. I mean, I would like to.
I think what people probably should think about is like a combination of two graphs here. One is the graph of the taxonomy, which has no real weight, as you said. I mean, this is always just the subclass of. It doesn't really make a difference between subclass of car, subclass of software. It's just a tree of
classification.
Yeah. But in your own world, in your own data, you have obviously different weights. You have a difference between, let's say a top-selling product, or this is a very high maintenance thing, or whatever. This is, then you can add the weights there. And then if you connect them with the standardized taxonomy data, and they say, okay, there's similarity here, but in my own data, in my own graph that is there, this node and this is much more important than this other one, then you calculate a different similarity score because it's added to this and totally.
I mean, it's true that taxonomies are particularly simple graphs because, they're not weighted in the relationships. They tend to be a tree, and there's no, it can be a directed acyclic graph sometimes, but they're kind of limited. But that, you're totally right, that does not impose any constraint on the richness of your actual data graph that you have. So this is a layer that you can add on top of your data, and that will help you in certain cases.
Then from Electron, thank you for this fabulous series. You're welcome. Hope you like it. Share it with your friends. Would it be possible to share the first 2 or 3 slides from Jesus' presentation, each of the episodes where you, Jesus, motivate the lecture?
Sure.
Is that on the GitHub repository?
No, we don't normally. That's a good point. I mean, I know, it's a single deck, so it should be really very, very easy. So look at that. We have the whole history from episode 1, 2. So I mean, I think we can put that somewhere. I mean, there's nothing. That's a very good point. Let me do that, because I suppose we can share that publicly in a read-only mode, and
we can
add
share
the
it with
link.
me, and I can chop it into individual PDFs or something, and add it to the GitHub repository. So under each episode,
it's like you have 70 slides already. Wow, I'm gonna write a book. That's gonna be
yes.
No, but good point. Yeah, that's we'll definitely add that.
Yeah, and that's a good point. From why, again, can we implement a Neo4j similarity with density feature? And I think you can.
Yeah, of course. I mean, this is
the graph data science library. You can.
Yeah, you can do it in graph data science. You can do it as procedures like we've done here. So it's an open platform to create. I mean, these methods that you've seen today have been implemented, and there's no reason why we could not take others or even be creative and come up with your own. So that's absolutely possible.
Yeah. I think another interesting question is, what if you have multiple paths between concepts? I guess that's another thing where you have maybe different ontologies.
That's I guess, because this approach only takes into account distance. The fact that I'm thinking of the case where you have 2 taxonomies and there's an overlap, right?
Yeah.
So maybe you have now 2 paths. As long as you don't come up with a shorter distance, I don't think multiple paths will happen. In these 3 particular metrics that we've talked about today, I don't think there will be an impact. But again, all these are features that are in your graph, and that we could explore, and we could come up with additional metrics. Yeah.
For example, when I had Sebastian Lobentanzer last week at the Neo4j Live, where we talked about BioCipher, and what they are doing is they are also combining a couple of ontologies together to find. So you can pick your own kind of builder, basically, and you decide what you're interested in, and then it's in proteins and genes and stuff like that, and they have like this cutoff point where they know, okay, this ontology only goes this far, but this other ontology basically takes on the journey from this end and goes even deeper. And I think with something like this, it would be very interesting to enrich this and to say, okay, I know the paths now. I define my ontology, and then I give
we could. So many ideas. We could squeeze it in an hour.
Totally. Exactly why it will have a big impact on practical implementations. I think you enrich with a standardized data set. You enrich your own data and help make clearer understanding of what's going on. Not necessarily. I mean, a recommendation is what we had now as a clear comes to mind. But I'm pretty sure there are plenty of other interesting things you can do with it. And if it's just knowledge management, knowledge enrichment, where you have ways of adding additional resources into your, let's imagine a search index kind of way. You look into your research papers, look into what's happening there, and then you add in a little side view additional information that came in through there, fitting to what you see on screen, for example. It's technically also kind of a recommendation, but also knowledge. Data, it's a different way of representing data, making data more accessible at the end.
Totally. I mean, I want to hear all these ideas, not just as ideas, but like, hey, I've tried that and that's what I got. So please, send us your comments on YouTube or whatever, the community or any channel, because it would be great to have this going both ways, not just one. But all great ideas.
Great ideas, great suggestions. Play with it. You said this week, so this latest edition.
So that's right. So the GitHub repo will be out today. You can, like I say, compile from source, but probably wait till the end of the week, and that will be included in the semantics release.
This semantics build, and then you can play with it, and then have our comments, have your comments, either like you said, put it on the community forum, put it under this video on YouTube. Just tag Neo4j, tag Jesus or myself, and to share what you built. And you know, I do regular live streams around all kinds of things. So if you build something cool, hit me up, and maybe you'll be maybe our guest or just my guest in one of our future episodes. So we can talk about it a little bit on this. Yeah.
Great. Well, it's been great to do it in person.
Yeah, it was really good.
Let's do another one soon.
A different dynamic. I think it's really great to do this in person. Hopefully, like you said in the beginning, it will take not another 60 episodes. Maybe
too
do
far.
this a little bit more.
2025.
Wow.
Let's do it.
Yeah, yes.
Now it's my turn to come to meeting.
Exactly. Yeah. With that, thank you all for watching. I hope you enjoyed this. If you missed any previous episodes of the Going Meta series, there's a YouTube playlist with all 16 of them. The GitHub repository has everything in there for all the episodes to follow through. We will take on the suggestion to add this the slide deck in the future, and try to maybe maybe redo that for the previous episodes as well. And yeah, this week, as a little outlook, on Thursday, it's May the 4th. So kind of Star Wars theme on Thursday. Michael will do another episode with ChatGPT as a co-programming guide. You know, I don't know, sabotage. I don't know what's going to happen on this on the morning, so Central European time in the morning. And in the evening, my colleagues Alison and Jason will actually talk about Star Wars, the hyperspace, pathfinding. Imagine you're a rebel and you want to plot a course across interdimensional space between the planets and avoid Empire, patrol or.
That's cool.
It sounds very cool and very interesting. They'll do this with Neo4j, obviously. So tune in then on the Thursday, and yeah, we'll be back next month. Most likely. The first Tuesday of the month, hopefully. Yeah. And yeah, with that, I wish you all a great rest of the day, rest of the week. And yeah, again, thank you for joining. See you next time. See you. Bye.